I'm Christina Welch, and this is a presentation over methanogens in cattle. So methanogens are in the domain Archaea. So these Archaeobacter are like all other Archaea in the fact that they grow in really extreme environments. So whether that be really hot or cold temperatures, really acidic or basic conditions, or high or low salt concentrations, they are generally always in really weird environments that most bacteria cannot grow in. So they cannot have oxygen, so they grow in anaerobic environments, and they are mostly found in gastrointestinal tracts of animals and also hydrothermal vents in the ocean. So one thing that's interesting about them is they are extremely difficult to culture, so therefore not much is known about them. But the three main types that are found in the rumen are the Methanobrevibacter, which makes up 61.6% of all of the methanogens in the rumen. And the two most numerous species of the Methanobrevibacters are Methanobrevibacter gottschalkii and Methanobrevibacter ruminantium. And another genre that's present in the rumen is Methanomicrobium, and also the rest of the methanogens that are in the rumen are in a group called the rumen cluster C, which is just an uncultured group of rumen archaea. So like I said earlier, they're extremely difficult to culture, and this entire group cannot be cultured, so they aren't sure what they are, so they've just put them in this catch-all group. And on the left you can see this is a picture of what a methanogen looks like when it is dividing out. So the pathway that methanogens use is called methanogenesis, and it's just the process of converting carbon dioxide to methane using hydrogen gas as the electron donor. So there are three different groups of bacteria that are involved in this process in the rumen. So the first is fermentative bacteria, and what they do is they hydrolyze the substrate polymers to simple soluble compounds, which are then fermented to BFAs, carbon dioxide, and hydrogen gas. Then after this step happens, obligate hydrogen gas producing acetogenic bacteria come in and oxidize the propionate, butyrate, and longer chain fatty acids, making acetate, carbon dioxide, and hydrogen gas. So then the last step of this is where the methanogens come in. The methanogens come in and they utilize the acetate and the hydrogen gas, and they take the CO2, and from that they produce the CH4, which is methane. Also, during this process, the rate limiting step is the degradation of the fatty acids. So breaking down all the really long chain fatty acids down to acetate, a form that can be used. So this picture is just a visual representation of methanogenesis in the last slide. So what happens is the cow eats the forage, so the plant material goes in down their esophagus into their reticular rumen, and the bacterial digestion / fermentation begins. And from this you get the hydrogen gas and carbon dioxide. And the methanogens take that and produce methane, which most of it escapes through eructation. So essentially the cow burps and they release methane into the air. Another way that this happens, if it happens in the hindgut, which takes place in sometimes in ruminants, but also in pigs and horses and all other animals that have methanogens, is the gas comes out the back end. So the reason that methane emission is a concern for people is methane is a greenhouse gas with a global warming potential of somewhere between 21 to 25 times that of carbon dioxide. So everyone in the world likes to say that global warming is happening, and they all want to blame the farmer for it happening. So methane emissions from agriculture represent 40% of the emissions from human-related activities. And from that 40%, cattle, sheep, and goats produce at least 86 million metric tons of methane per year. So since methane emission is such a concern right now, science is really pushing to find a solution to this problem. So some of the possible solutions are changing the dietary composition of the feed, so increasing the hemicellulose and starch, and decreasing the cell wall components, and increasing grinding. The only thing with this is it would increase the passage rate and increase the propionate, which in turn would decrease ruminal pH. So instead of fixing the problem, it would just shift methanogenesis to the hindgut fermentation instead, and also pose a risk of acidosis. Another option is using lipids in the diet, so fatty acids, tallow, seeds, and oils. So this would essentially inhibit protozoa and methanogens. It would also increase propionate, and it would affect the palatability of the food, perhaps the performance, feed intake, and the milk components. Another option is defination, using either chemical or feed additives, and this would just remove the associated methanogens and create less hydrogen for methanogenesis. The only concern with this is that the microbiota would eventually adapt and learn to deal with the less hydrogen, but continue to perform methanogenesis. Another option that they're thinking about using is methanogen vaccines. So the problem with this is they would use the host immune response. However, they aren't sure how that they would get it to target the methanogens. Another option is using antibiotics like monosin. It would inhibit protozoa and gram-positive bacteria. However, the microbiota could essentially adapt to the change in the environment, and also this antibiotic is banned in the European Union. Another option is using plant compounds such as condensed tannins, saponins, and essential oils. However, this antimicrobial activity would reduce hydrogen availability. However, there's an unknown dosage, and it could affect digestibility. And lastly, they potentially thought about using organic acids, so furamate and malate, which are hydrogen sinks. So they would also increase the propionate and affect digestibility. One thing that's overarching is most of these would vary based on diet and species, and that all of them would need more research before they could go on the market. So one thing is methanogens are not all bad. They need to decrease the amount of methane produced, but methane is needed in the rumen. It helps increase ATP production. So when you go from glucose to pyruvate to acetate, when you add in methanogens, you get 4 total ATP instead of 3. Another is scientific articles have found that there is an increased performance in cattle based on methanogens. So one study found that steers with positive residual gain had more numerous methanogens than those with negative residual gain. And a different study found that Methanocephala and Methanobrevibacter strain ABM4 were more abundant in less efficient animals. So if you take the less efficient, if you remove those, then perhaps there's a chance of having more efficient animals. And these are all the references I used, and thank you very much.